Hello! For the second part of Lecture 2, we will focus our discussion on the different chemical reactions that we will encounter in this course, and then review some basic stoichiometric calculations. So let's begin with familiarizing the different types of chemical reactions. A chemical reaction happens when molecules of substances or reactants collide with each other with enough energy that would cause the rearrangement of particles to form different compounds or products. Take note that only new compounds are formed in a chemical reaction and not new elements, which happens in a nuclear reaction. You have already been introduced to the concepts of thermodynamics in Eng 201, which generally describes the changes in energy when a reaction takes place. Another concept that is introduced here is kinetics, which identifies the rate or speed at which a reaction takes place. One type of chemical reactions are gas phase reactions, which happens when gases react with other gases, liquids, or solids to form new products. Examples shown here are the formation of water by the reaction of hydrogen and oxygen. And then another one is the reaction of methane with oxygen to form the combustion products CO2 and hydrogen gases. However, most of the chemical reactions that we will study in this course involves reactions in aqueous solutions. First is the acid-base reactions, or what we call neutralization reactions. Generally, a neutralization reaction happens when an acid and base react to form water and salt. In this example, nitric acid reacts with sodium hydroxide to form water and sodium nitrate, which is completely ionized in solution. Precipitation reactions occur when an insoluble compound is formed from the reaction of two solutions containing soluble ions. The solid product or insoluble compound is known as the precipitate. Precipitation reactions may be predicted by knowing the solubility of the compounds that will form in the solution. For example, combining sodium iodide and lead nitrate yields the insoluble lead iodide precipitate and sodium nitrate, which is soluble in solution. Oxidation reduction or redox reaction is a type of chemical reaction that involves the transfer of electrons between two species, thereby changing the oxidation number of a molecule, atom, or ion. An example shown here is the reaction of ferric oxide with carbon. This redox reaction caused the oxidation number of iron to change from positive 3 to 0 and for carbon from 0 to positive 4. Complex formation reactions, as the name implies, are reactions that yield complex ions or molecules as products. A complex ion or molecule consists of a central metal atom that is surrounded by other atoms, ions, or molecules with a lone electron pair. These different types of chemical reactions will be further discussed in the succeeding lectures of this course. Now we move on to the last section of Lecture 2, Chemical Stoichiometric Calculations. Chemical stoichiometry is the quantitative relationship among the amounts of reacting chemical species in a given reaction. Before we begin with the calculations, let us recall some of the terms used. First, we have the mole. It is the SI unit used to indicate the amount of chemical species. 1 mole of a substance is equivalent to 6.022 times 10 to the 23 atoms, molecules, or other elementary units. Recall that 6.022 times 10 to the 23 is Avogadro's number, which is used to convert from number of moles to number of particles and vice versa. Next is molar mass. This is the mass in grams of 1 mole of a particular substance. It has a unit of grams per mole, but it is also numerically equivalent to the atomic mass, or AMU. Example, the element oxygen has an atomic mass of about 16 AMU and a molar mass of 16 grams per mole. Also, recall the difference between empirical and molecular formula. The empirical formula gives the simplest whole number ratio of the number of atoms in a particular chemical compound, while the molecular formula identifies the actual number of atoms in a molecule of that compound. For example, acetylene has a molecular formula of C2H2 and benzene is C6H6. If you simply look at their empirical formula, which is CH, you won't be able to differentiate between the two compounds. Next is the difference between formula and molecular weights. The formula weight is the sum of atomic weights of the atoms in its empirical formula. On the other hand, molecular weight is the total atomic weights of atoms in a molecular formula. Going back to our example earlier, acetylene, which has a molecular formula of C2H2, has a molecular weight of 26 grams per mole. Its formula weight, however, is just 13 grams per mole. If you divide the molecular weight by the formula weight, you will get the whole number ratio that must be multiplied to the empirical formula to get the molecular formula. Now let's move on to stoichiometric calculations. You have encountered in your N201 course the calculations involving mass to mole to particle conversions and determination of limiting and excess reactants. In this lecture, we will revisit these calculations and also introduce problems involving simultaneous and consecutive reactions. Stoichiometric relationships of chemical species in a reaction usually involve looking at the number of moles of the reactants and products. This results to necessary conversions because the known information are normally given in mass. To convert from mass to moles and vice versa, you have to make use of the molar mass. And then to convert from moles to particles and vice versa, you use Avogadro's number. It is important that you make sure that all units used are consistent and agree with each other to make the calculations correct. As an example, calculate the number of millimoles of benzoic acid contained in 2 grams of pure acid. To solve this problem, convert the given mass of 2 grams to moles by dividing it by the molar mass, which is 122.1 grams per mole, and then convert to millimoles as the problem requires. This will give us 16.38 millimoles. For determination of limiting and excess reactants, let us consider this problem. Soda fizz comes from sodium bicarbonate and citric acid reacting to make carbon dioxide, sodium citrate, and water. This is the reaction. If 1 gram of sodium bicarbonate and 1 gram of citric acid are reacted, which is limiting? And how many moles of the other reactant was in excess? The first step in solving this problem is to establish the balanced chemical equation. Since the equation is already given and balanced, we can proceed to solving for the first required. So if 1 gram of sodium bicarbonate and 1 gram of citric acid are reacted, which is the limiting reactant? Recall that the limiting reactant pertains to the compound that limits the amount of product that can be formed. This means that when the limiting reactant is fully consumed, the reaction will stop and the compound that still remains is what we call the excess reactant. To determine which of the reactants is limiting, we have to calculate the amount of product formed when each of the reactant is consumed. Whichever produces the lesser amount is the limiting reactant. To determine the limiting reactant, you don't need to calculate the amounts of all products formed. You just need to choose one. For this case, let's choose CO2. If sodium bicarbonate is fully consumed, the amount of CO2 produced is obtained by converting the initial mass of 1 gram to moles by dividing it by the molecular weight and then multiplying it by the stoichiometric ratio of CO2 and sodium bicarbonate. Recall that the stoichiometric ratio is the ratio of the coefficients of particular compounds in the balanced reaction, which we use to convert amounts of one substance to another. Calculating, we get that 0.0119 moles of CO2 is produced for every gram of sodium bicarbonate. Doing similar calculations for when citric acid is fully consumed, we get 0.0156 moles of CO2 produced per gram of citric acid. Comparing the two values, we see that fewer moles of CO2 is produced from sodium bicarbonate and therefore that is the limiting reactant. For the second question, how many moles of the other reactant was in excess? First, calculate the moles of citric acid that is initially present by dividing the mass of 1 gram by the molecular weight. This gives us 0.00521 moles. Second, calculate the amount of citric acid reacted. We already know from the previous question that when sodium bicarbonate is fully consumed, it produces 0.0119 moles of CO2. Therefore, we can determine the moles of citric acid reacted by multiplying the moles of CO2 by the stoichiometric ratio, and then we get 0.00397 moles of citric acid reacted. Finally, the amount of citric acid in excess is obtained by subtracting the moles reacted from the initial amount. The excess amount of citric acid is 0.00124 moles. If you're interested to get the equivalent mass, just multiply it by the molecular weight and it shows that 0.24 grams of citric acid is left after the reaction. Lastly, we move on to simultaneous and consecutive reactions. Simultaneous reactions are two or more chemical reactions that occur at the same time and in the same system, while consecutive reactions are those in which the product of one reaction becomes the reactant of another reaction. To further understand this, let us consider this problem. Phosphoric acid is a very important compound used to make fertilizers. It is also present in cola drinks. Phosphoric acid can be obtained in two steps, as shown in the two reactions. Excess oxygen was reacted with 272 kilograms of phosphorus to form tetraphosphorus decoxide with 89.54% yield. In the second reaction, a 96.8% yield of phosphoric acid is obtained. How many kilograms of phosphoric acid is obtained? Again, the first thing you do is to check if the given reactions are all balanced. A reaction that is not balanced properly results to wrong stoichiometric ratios and thus affecting the whole calculation. Next, calculate the theoretical yield of tetraphosphorus decoxide from the first equation. The theoretical yield is the amount of product when 100% of the limiting reactant is converted. Since it was mentioned that excess oxygen was used, then we use the given amount of phosphorus to get the theoretical yield. To calculate, first convert the given mass to grams and then divide by the molecular weight to get the moles of phosphorus. Then, multiply by the stoichiometric ratio to get 2,193 moles of tetraphosphorus decoxide produced. Next, get the actual yield by multiplying the theoretical yield by the given percent yield of 89.54%. We get the actual yield of 1,964 moles. This is the amount of tetraphosphorus decoxide that will react in the second equation. Similar with the calculations done in the first reaction, first get the theoretical yield of the second reaction, then the actual yield based on the given percent yield. The actual yield of phosphoric acid obtained is 7,605 moles. Converting this to mass in kilograms, we get 745.29 kilograms of phosphoric acid produced. So this ends lecture 2. Thank you for listening.